on an analytical approach to differential equations. And now in the last video, I left off with this one problem that says the population of a species is initially 288 and has a growth rate that depends on its population, given in this table. What that means is the greater the population, the faster it grows. Find a function that models its population with respect to time t. And I left this hint to try and graph this, graphing the population on the horizontal axis and the vertical axis where you would want to graph the growth rate. So I did that, and this is the picture that I got. And you can see here, population versus population growth exhibits almost a perfectly linear equation. I ran linear regression, and this is the equation that I got, and for this particular graph. And you can see that r squared is approximately 1, so that means the correlation is practically perfectly linear. So from here on out, the work is all logical and mathematical. So let's see, what do we know? We know that first, population and its growth rate are linear. Okay? In other words, P of t and dP over dt has a linear relation. Next, if you look at this image here once again, you can see that not only is its correlation linear, the y-intercept is practically 0. It's very, very small. So we can estimate it to be about 0. So that the y-intercept of the graph of P of t versus dP dt is approximately 0. Now I'm going to show you later that it doesn't matter even if this is non-zero, but for this problem, let's just approach it as though it was almost 0. So then what we can take away from here is that dP dt differs from P by a constant. Right? This is what we call a power function. Okay? In Algebra 2 or maybe in pre-calc, you learn what a power function was. So it differs, it's related to each other by the multiplier of a constant. Okay? And actually, from this point onwards, we can figure out what P of t is equal to. And to go from this point on, it's not much different from what we've done before. We start out by separating variables, and then integrate. So we get dP over P is equal to K dt. This is really 1 over P dP is equal to K dt. And remember, K is a constant. And then integrate. So on the right-hand side, we have kt. On the left-hand side, we have the natural log of P. Let's just be very clear here. The natural log of the absolute value of P plus a constant. And remember, there's a constant over here too, but we can just move it to the other side because a constant plus a constant is still another constant. We can remove this absolute value symbol because the population is always positive. Okay? So we don't need to worry about negative population. That doesn't make much sense anyways. And now we want to solve and get something like P of t equals something. So we're pretty much close to getting that done, converted into exponential form. So you have e to the kt plus c is equal to P. Now this e to the kt plus c, that's really e to the kt times e to the c equals that. And then this right here, e to some constant, is also a constant. So finally we can write this as c e to the kt. I would call this c1 here just because, to differentiate it, to make it a distinction from c. It's not really a big deal, but it is a different constant, is equal to P. and we want to write this as a function. So this is P of t is equal to C times E to the kt. Now, let's take a look at a big picture of what we've done here. We started out with some data, and this data tells us nothing about time. It doesn't say anything at all about time. All we know is this is the population, and this is the growth rate of that population. Okay? And we know that the bigger population you have, the faster the growth rate is. But it doesn't tell us anything about population versus time. But we can use what we had in the chart, set up a differential equation here. Okay, set up differential equation here. Okay, and then use the techniques that we've been using to figure out the rest. Now, there's one more part to this problem, is that we haven't actually found a specific solution yet. We need to figure out what these constants are equal to. Okay, we need to figure out what C1 is equal to and what K is equal to. So to do that, we have to use the initial condition that we have here. That means that when t is equal to 0, P of t is equal to 288. Okay. And then we could also use this fact here that when P of t is equal to 288, dP dt is equal to 95.76. Okay. So let's go back to the equations that we have. We have dP over dt is equal to K times P. Making these substitutions, we have 95.76 is equal to 288 times K, which means that K is equal to 0.42. Okay. So that's an important fact that we get to use. Then we're going to have to figure out what C, or C1 here, is equal to. So we use the other equation that we have. P of t is equal to C1 e to the kt. Okay. But we already know that K is 0.42. And now we're going to use these 2 points. So 288 is equal to C1 e to the 4.42 times 0. This part here is 0. E to the 0 is 1. So that 288 is equal to C1. Okay. So finally, our complete answer is that P of t is equal to 288 times E to the 0.42 t. Okay. Now, you may think that this seems familiar, that you've seen this somewhere before, and in fact you have. You've probably seen this in pre-calc. You've definitely seen this in pre-calc, and you may have seen this in algebra 2. Okay? Because this is an equation. Let me go back to this equation actually. Let me go back to this equation right here. This right here is an equation for exponential growth. Okay. And then one quick note here. If K is negative, then we have exponential decay. Right. So you look back at some of the work that you did in algebra 2 and some work you did in pre-calc. This is actually the process for how exponential decay and exponential growth equations came about. People started with a problem like this, trying to find an equation that explains the growth of a population, and just working through the logic and the data, it gives us this result. Okay. So hopefully you are able to follow that and understand a little bit more about where this stuff comes from. Thank you for watching. Have a wonderful day.